go. Floor is yours, Felipe.
All right, let me share my screen. And one chance for you to mark your Zoom bingo. Can you all see my screen?
Yes, we can.
Okay, I'm not sure if you can or you cannot see my screen.
Yes, we could see your screen.
I cannot see you or hear you.
Oh. We can see your screen. I don't know if you can hear me.
Oh, I can hear you now. Thank you.
Okay, great. Yes.
All right, so this is the data access tutorial. I usually like to start this tutorial by saying that we have a lot of servers, a lot of data everywhere, but it's like water everywhere, not a drop to drink. It's servers everywhere, but not a bit to flip, because it's hard to actually find the data that you need and that you want. And there is bit rot everywhere. So I can share a URL with you today. You can try to access it 1 year, 1 month from now, and then the data is no longer there, or the data change, or the metadata change, or they updated the QA/QC and you don't know, and your results are either you cannot reproduce or you reproduce them without noticing that something is wrong. All right, so who am I? My name is Filipe Fernandes. You can find me online as OCFPF everywhere. I'm a physical oceanographer, and these are a few names that I collect that people call me. I'm a data plumber because I usually help the data get to the user. I'm a code janitor because I go around fixing, not really fixing, but trying to make other people's code look better and easier to maintain. A continuous integration babysitter. Continuous integration is usually what we do to test our code on our pipelines of data. And I watch them, and if they fail, I go there and I fix them. And I'm also the package dash button for CondaForge. CondaForge is the conda channel that we use to install all of our packages. And pretty much I was one of the first scientists there and helped created it. So people kind of rely on me to add packages there. I do have a day job, though. I don't do this for a living. And my day job is I work for IUS, kind of indirectly. Mostly I work for the Secura, the Southeast Coastal Ocean Observing System. And there's all mouthfuls, all these acronyms, but they are regional associations that collect data locally and kind of ship them upstream so we can easily access them. There's a very, very simplified way of explaining what IUS and the regional associations are. But in the interest of time, I'm going to leave it at that. But if you have more questions, please try to find me or Matt Peter, who's also on the line, and we'll be more than happy to answer your questions. So big data or small data, we need it. There are various sources from a variety of servers, APIs, web services. We can host our data on FTPs, HTTP or HTTPS, S3, live access servers, and whatnot. By the way, if you know what live access server is, like me, you should probably be about thinking of a retirement. And if you don't, be glad. It's kind of hard when I can't see the audience. Like either all my jokes are terrible or people are laughing and they're muted. I'm going to take the second one. I'm going to believe the second one, even if it's not true. All right. So before I start the tutorial, I want some feedback from you. I want you to keep these 4 points in mind as you watch my tutorial. So I want to improve this. And for the future, where should I focus on? Leveraging metadata to find and explore data, the software packages to slice, dice, and analyze the data, or the data sources, or none of the above. Maybe you don't need this tutorial. Please keep that on the back of your head while you watch this tutorial and send me some feedback at the end. All right, so we have many web services and type of services, and this is just a few. There are more common ones. Usually for time series like in-situ data, buoy data, and stations, we have the Open Geospatial Consortium, SOS, this, I'm completely drawing a blank, the sensor observing system. This one is even though it's an OGC standard, it's kind of been phased out for oceanographic data. And it has an XML response, which is metadata rich. And we have a comma separated value response, which has less metadata. It's usually lossy. So we lose information, but it's easier to load and parse as well. For gridded data, usually ocean models and satellite images, most of the time we use Opendap, which has a binary response, but many softwares can read this binary response to give us a high-level object with all the metadata and etc. that we need to understand the data. For raster images, like satellite images from the visible channel, for example, we use the OGC standard WMS, Web Mapping Services, and these are GeoTIFFs or PNG or JPEGs that we can easily navigate and even create apps from them. And I'm going to talk a little bit about those in this tutorial. And then we have Erdap, which is pretty much eating all of these and became probably the most common data service out there. It has a RESTful API. The responses, like your imagination is the limit. You can have pretty much any response you can imagine, it's there. And this is what makes Erdap really, really flexible and useful. By the way, for raster images, there's also Stack, where you can find raster images. And not to forget, we have cloud buckets and various other formats and ways to put your data online. Okay, so what we're going to see in this tutorial, we're going to see Erdap, Opendap, which are the most common ones. We're not going to see a SOS because that's being phased out, but we're going to see a substitute, which is an Erdap server for most of the SOS data that used to be served in this format. We're going to see very briefly the web mapping services, and I'm going to touch base very briefly on CSW and CCAN. This is the catalog service for the web. I'm drawing a blank for what CCAN means, but pretty much they're both catalogs for data, where you query the catalog, and the catalog gives you the URL to access the data. There are many examples in the iOS Code Lab for those two. All right, let's start. So Erdap. Our learning objectives here is going to be, we're going to explore the Erdap server using the Python interface. I believe there is a Julia interface now. You can use the web interface. There is an R interface. So there are many ways you can access Erdap. Pretty much we're going to find a time and a region of interest and download the data for that area and that time and create some plots. So what is Erdap? I kind of already hinted into it. We have this flexible output, and this is Erdap probably best feature ever. If you want an HTML table, you got it. If you want an Esri ASCII format, you got it. Comma separated file to put it on Appendix, you got it. This is a modified version of the comma separated file that has more metadata, pretty much the units. You got it, KML. You can even have an Opendap, so you can substitute all your Opendap servers for Erdap servers and have all this for free. And suppose you're still a MATLAB, you can have a MATLAB response and load your data on MATLAB. NetCDF or the Ocean Data View format, if you wanted to use that, so on and so forth. Probably the most interesting ones are the JSON one that you can use to create a web app, the comma separated values ones that you can load on Pandas, and the Opendap one. It has a RESTful API to access the data. So you pretty much build a URL with your query, and then you query the server. The server slices that for you and sends you back the data. So it's a server-side slicing. And this is great because you don't need to download a huge chunk of data to then slice it, right? You can be smart and download a subset of the data. And another beauty of Erdap is that it standardizes all the dates and times in your results. So you don't have to deal with multiple time formats. All right, so this is a typical Erdap query. You initialize the Erdap class, you feed it the server. This is an optional one where you can put the protocol, but you can omit that if you don't know the protocol yet. And that's it. You just initialize the server object. Now that you have the server object, you can try to find what services do you have in this Erdap server. In this case, it's pretty much all table dap. Table dap is data in a table format. The grid dap, it's probably closer to what Opendap is, even though you can have an Opendap response for both, but you can do server-side slice with this one. And you can even have WMS inside an Erdap server too. So it's really like the one ring to rule them all. So okay, let's query something. So in this case, in this example, we're going to use the standard name, seawater practical salinity to query for data. Erdap has this categorized URL where you can create a URL categorized by some sort of key value standard. So the key is going to be standard name, and the value is going to be seawater practical salinity. And we want the comma separated value response. So this creates a URL with all the data that has seawater practical salinity within this metadata key, standard name. So we found 379 data sets. That's a lot, right? So pretty much all the data sets that we have in this server have salinity in them. And I know that for sure, because this is, if I'm not mistaken, glider Opendap server. So all these gliders have some sort of CTD with temperature and salinity. So let's narrow down our search a little bit. We don't want all the data sets. Let's say we want salinity within a certain latitude and longitude and time extent. We could create a latitude and longitude bounding box. This is pretty much a rectangle. I'm just going to use IPyLeaflet to visualize that rectangle. So this is our rectangle here. I want all the salinity data within this rectangle, right? And then we can create a Python dictionary like this. The starting time, the end time for a query, our rectangle, and the metadata for the standard name of salinity. And there you go. We just feed that dictionary to the search URL. And now it's definitely more manageable. We have 36 data sets within that square. And these are all OI gliders that we have there. That's much better, right? We reduced a lot our net that we're casting to find data. So suppose you have an experiment within that area that falls within that time range. That's how you get salinity. Now let's expand a little bit. Let's get more data. If you feed them all the variables that you want, and here I'm using salinity and temperature long names from the server, I'm gonna get data for the first glider, the first data set ID only, and I want depth, latitude, longitude, salinity and temperature, and time. You already noticed at this time that all that Opendap does is to build URLs, right? And here I can click on this URL and find the data. This is this first glider here, OY, CP02, PMCY, and etc. The default response when I don't specify one is the HTML one. And here's all the variables that I listed. So this is the RESTful API that comes for free with Opendap. And if I click on this URL, I'm taken to the Opendap page where I can see more information. For example, I can see that all the variables that I selected are ticketed here, right? I can change the response here if I want to explore, or I can click for more variables. I can change the constraints, and I can even create a plot from this web page. I just wanted to show you the link between the RESTful API and what we're getting here on the Python side. But you can do that all manually if you want using the web interface. All right, so let's try to download some data finally. Now that we searched within a certain area, we narrow it down to a single glider for now. We're going to get more gliders later. So we can use pandas, and in this case, the Opendap has a method to pandas for us, where I can set my index to be the time, and I can ask it to parse the dates for me, and I can drop another number just to do some chaining operation here, and voila, I have a table with all the data in all those variables that are requested. Pretty cool, right? And we have some metadata within the comma separated value response, like Z is meters, latitude and longitude are degrees, salinity is 1 to the minus 3, which is per mil, if I'm not mistaken, and degrees Celsius. So we have some metadata, not a lot, but still enough to understand this data. This is an exercise that I will leave for you to do on your spare time. There is also 2xArray method. Try that at this point and see what kind of object you have and what kind of metadata you have there. Usually when you use one or the other, spoiler, when it's stable, use pandas. When it's more than 2 dimensions, use xArray. All right, so let's do a subset of that data frame. Let's get like the bottom of this glider depth, like all the minimum depths that we have throughout the data frame, because I want to see the bottom salinity. So I do a trick here where I get the Z, where the Z is minimum, and I filter that subset and I plot. So this is my salinity at the bottom for this particular glider. The glider, I'm not sure if you're familiar, it dives in a Z form. So the depth is not homogeneous. So the depth here is not exactly the same. So try not to interpret this as the bottom, but as the minimum depth, where the actual maximum depth where the glider dove at that particular time. And we can do a TS diagram just to explore the data. This is a typical coastal TS diagram, very constrained. We can see some data outside of this cloud here. This is probably something unusual, either storms or, I don't know, we need to check data from a different time period, or like some sort of warming. It would be nice to investigate why we have so many outliers here. All right.
Filipe, can I interrupt you?
Yes, please.
We have a question in Slack. Is there any effort to create any across-server functionality for ERDAP querying or dataset cataloging? Or would someone need to check each server independently for datasets that might contain variables that might be of interest?
Yes and yes, there are efforts. Say, for example, if you want Argo data, it searches many servers. There is a package called GliderPy that searches many servers for gliders. So things are kind of specific to a certain data type. But there is also, for example, with ERDAPI, one project that didn't start yet to search the IUs arrays. There is multiple servers search within ERDAPI, so you can search all the servers that's listed on the awesome ERDAP list. I'm gonna get to that. But you need to be careful when you do that, because I believe there is a package, if I'm not mistaken, in NAR, where when you do, you always search a curated set of ERDAP servers. But if a particular server is not there, well, the user may be tricked into thinking that that server doesn't exist because the list is not readily available. It's kind of hidden to the user. So ERDAPI is kind of lower level. It's the tool they're going to use to build the tool to do that, right? And there are many projects that do that. Another one that we're going to see here is called Survey, and we're going to see later in my tutorial. It uses ERDAPI to search a curated set of servers to get co-ops data and the ICO data as well. So sorry if my answer was confusing, but the thing is, yes, there is a few efforts, but you have always to be mindful on what list of curated servers that you want. And if you want to do that yourself, ERDAPI has the functionality to do parallel searching for you. Any follow-up, Paige? I can't really see the chat.
No, that was great. There are a few other posts responding to that question that have a few links that might be of interest as well. So I'll point people there, but thank you.
Okay, so I have a small exercise here where I ask you to change that server and to this one and try the same search and see what you can find. And this kind of goes, it's a good segue for that question, because sometimes different servers may have the same data. And if you're not mindful when doing that, you can have duplicate data without really knowing, because the metadata can change from one server to the other. So yeah, this was an excellent segue for that question. Whoever asked that, thank you, I owe you a beer. All right, so Opendap. Any other question on ERDAP before we move on? Go once, going twice. All right, so Opendap is probably older, but still going strong kind of way to serve your data. You can serve your data, your gridded data in ERDAP, but it shines with table. You can serve table data in Opendap, but it shines with gridded data. So it's not that one is better or than the other. It's pretty much they complement each other. That's why ERDAP has an Opendap response. The most common way of accessing Opendap is via thread server. And in our learn objects here, we're going to do that using Xarray. We're going to try to discuss the difference between an ERDAPI request and an Opendap request, and then we're going to plot the data that we requested using the Xarray plotting interface. So the very first thing that we're going to do, I don't like raw Xarray. I like the CS Xarray. And this is a package that Deepak created that leverages the climate and forecast metadata and allow us to do some more high-level queries. In this case here, I'm getting the ROMS model from the Rutgers group, from the Doppio program. and I'm getting the best simulations time series that they have. What I do for Opendap, I feed Xarray the Opendap URL, and I get this AIDS object. I did not download any data yet. The only thing that I downloaded are the coordinates and the metadata. So maybe this is the main difference from ERDAP. In ERDAP, I also get a lot of metadata and lazy evaluation, but when I slice and request the data, I get all the data. That's why you do your slicing first. With Opendap, you do your slicing afterwards. You get all the metadata, you inspect it, and then you slice, and then you request the data. So here we go. Looking at the CF metadata, we have all these nice X, Y, Z, T coordinates. This is a ROMS model, and if you're familiar with a ROMS model, you know that we have 2D X and Y. That's why it couldn't be defined here. So we have the side grid, the row grid. It's also 2D in the vertical. We have ocean time, which is the forecast, and then the real time. And the best thing about the CF metadata, in my opinion, is this. The variable names are not standardized. It can be pretty much anything. And some oceanographers are pretty familiar with this variable. I know that U velocity, V velocity, and W velocity, but let's say I don't know what zeta is. And what's U eastward? Like, what's the difference between this one, right? Or U bar. And using the CF metadata, I can come here and see the standard name and read about that. So U bar is the barotropic eastward velocity. Zeta is the sea surface elevation anomaly. So I can have like a more high level inspection of the metadata using the CF metadata from CF Xarray. And by the way, if you didn't notice, here is just the standard Xarray request. The CF Xarray, when I imported it, it augments the Xarray object with the CF method here, let's say, or the CF accessor. If I don't import CF Xarray, this doesn't exist. But CF Xarray per se is not something that we import and run. All right, so here's probably the most Frankenstein slice that I ever made, but I did that on purpose because I want to demonstrate 3 different aspects of Xarray that you can use to slice an Opendap server. So I'm using a CF standard name to get temperature. And then I'm using the Xarray cell, the selection, to do a high-level time slice. So I want the 2022, 810. And then I'm using the I cell, the index selection, to get the surface. In a ROMS model, the surface is the last grid point, not the first. So I mixed the 3 different slicing just to show you how Xarray with CF Xarray can be powerful. Ideally, in the future, we should slice everything using high-level syntax in the CF object. But for the vertical coordinates, for example, the support is still experimental and doesn't work exactly how we want. But we're going to improve on that. And then we can plot it. So this is the surface data for this particular model. And it wasn't really hard to slice it and download. And when I made this kind of selection here, it's actually just a few megabytes. I didn't really download the whole time series of ROMS model that Quanticus have, because if I do that, I'll pretty much blow up my RAM memory here. It's a lot of data. So that's one of the nice things about using Opendap as well. You inspect the metadata, you slice what you want, and then you download it. All right. Any questions on Opendap? Going once, going twice. All right, SOS serving. So like I said, SOS is no longer something that we should be using. It's being phased out, but the co-ops data used to be only on SOS. Thankfully, they moved all their data to ERDAP, but it's not really easy to access the way they created their ERDAP server. But we're lucky. There is this package called Survey, which is a plain word for survey at sea, that wraps their ERDAP server and allow us to do a high-level query using ERDAP Pi under the hood and the co-op servers. So this is one of servers aggregators out there. So how can we do searching using Survey? Say we can create a bound box like here. It's very similar to ERDAP Pi. You actually use ERDAP Pi under the hood. And then we query, like this is the bounding box for the Secura region, one of the region I use region associations. And then within these co-op stations within a region method, we can find all the stations that exist for Secura. We even have the status active or inactive in case we want to filter out those that are no longer collecting data. But this is pretty cool because we have the NOS ID, the NWS ID, the National Weather Service. We have the name, the state where the station is located at, the status, some of the endpoints of the times, and their position. So it's pretty nice that we can easily inspect co-ops data like that. We can even select a station using high-level names, like this is the duck station for North Carolina, and suppose you were talking with a fisherman there and he knows the duck station, and you want to figure out, whoa, okay, I want the NWS ID for that because I want to find that data. You can just try to look for it. And this is the duck station. And it's actually active, and it's located around this point here. And then if you want data from the duck station, you can select a time range, use the co-op station method, and ask for it. Here I'm using a Python trick starting from today and 15 days prior. So I want the past 15 days time series. I want the elevation, the water level. And this is the water level at duck station. So pretty much tides, nothing interesting. But if you do this during a hurricane time, usually this area has some very interesting water elevation to look at.
We have a
Any question on survey and how it wraps ERDAP Pi to access multiple servers?
Yes, there is a question that actually doesn't have to do with SOS specifically. Is there a distinction between how users should approach using Xarray to load data from Opendap versus ERDAP if the goal was to keep the processing on the server side? Or does Xarray handle that?
Xarray doesn't handle the server side for you because Opendap doesn't handle server side. So no, if you want to do things on the server side, you need an ERDAP server. However, Xarray is smart enough to never download the data until you slice it and reduce it enough to make, let's say, a safe download, right? A download that the server and your computer can handle. But yeah, there is no lazy slicing for Opendap. There is an old syntax for Opendap where you can provide a pre-sliced URL, but I don't think Xarray supports that because, well, actually Xarray does support that because Xarray supports multiple Opendap backends. But the NetCDF4 backend doesn't support that. If you're using the PyDap backend, it may work, but it's very clunky because you need to index with integers. It's not high-level slicing. So you need to know the stride for data, say from index 0 up to index 100, which makes it so awkward that it's probably easier to just download the metadata like I did, inspect the metadata, slice it, and then request. If your request is too big, you can request in chunks so you don't hit the server too much. Does that make sense?
Yeah, I think that was great. We do have another question that's about CF Xarray. This person says, if I understood it right, it means that CF Xarray kind of does a CF convention check to standardize variable attributes. In case our data is messy, what is your suggestion to transform our metadata to agree with CF standards?
Matt is asking those questions, right? I'm going to check the chat log later, but I'm pretty sure that's Matt. Okay, so yes, let's take a step back. CF Xarray does leverage with CF metadata, but it's not as strict. So if your data is messy, you can still load it. You just can't use it. If you're using Iris, which is more strict, then you're actually going to fail. But say you want to fix your data, there are many options. The first one is use some sort of compliance checker, and I use compliance checker to do that. And then you can fix your metadata for good, like at the lower level of the data provider. That's probably the best option. The second best option is to create a layer on top of your data, say using MCML, which is an XML syntax where you patch your metadata. So your model is not CF compliant, but then you patch it before you put it on the server. That's probably the second best option. And the third option is to create callback functions. And CFX-Ray doesn't support that yet, but they're planning on it. But Iris does, where at load time, when you're loading your data, you patch it. Why I'm saying that the first one is better? Because you're fixing it for good and for everybody. Why the second one is the second best? Because you're fixing it early before the user gets the data. And why the third one is probably the worst, but sometimes we have to do it because you're fixing it only for yourself and not for the whole community. Does that make sense?
Yes, thank you. And for reference, it was not Matt who asked that. So you can go back later. But thank you. I think that answers it. Okay.
So WMS, this is just a very quick example on how to use WMS to create a hurricane visualization widget. I'm going to be using IPy leaflet, and just never mind the imports here. Like it's not too complex, and I can go in details if you're curious about this later, but I'm creating a widget that's going to search for these times here on the WMS server. And then I'm going to plot a map from this URL, this WMS server, which is radar data. And then when I post my map here, I can have this widget, and I can just slice the widget and see the different images getting loaded there. As you can see, let me maximize here. Okay, so this was actually a hurricane that hit this area a while ago, and we can create an animation of this hurricane using this widget. It's just a few lines of code. It's pretty cool. This is very, very handy for data exploration, not necessarily for science per se, but because you can have this within an Opendap, a thread server or an ORDAP server, it's always nice to enable that so people can easily explore the data before they go in there and download it. All right, the last one, the catalog service for the web, CSW. So I have a question. Is there a canonical source of data? Okay, I'm going to tell you. I don't know. And this is usually where I should cut my connection and run away, because this is a hard question. There is kind of. The closest things that we have is the IU CSW catalog. Now there's the Pandil Forge. There are other catalogs out there, but the more you try to aggregate the data and become a canonical source, the harder it is to standardize the metadata, to have everybody be compliant with the rules of having the data there. And also your server starts to scale to sizes that becomes unmanageable. Even if you defer that to multiple servers and you just accumulate the actual endpoints. And this is what CSW does. It has a very nice Python interface, the OWSLib catalog service for the web. Like I said, the IU's Code Lab has many examples of this. I'm not going to show you one here. You can do advanced filtering, which is like time, space filtering like we did here, or with variable names. You can do some really, really fancy filtering to get the data that you want. And the very interesting thing about this is that you don't actually get the data. You get the endpoint of the data. You get where the data are, not the actual data. And then with this information, you can download the data. This is just a scheme where you can have multiple servers that are harvested every night. Things are standardized and then synchronized with the Geo portal, and then you can create a catalog from them. So it's like those old phone books that pretty much no one here saw one, except for those that are my age or older, where you can find where to find the data. Please look for examples on the IU's Code Lab page. We have the link here, and you have the slides. And well, still the question remains where I can find data. So if you're looking for AirDAP servers, there is this curated list of AirDAP servers at the awesome AirDAP. If you click here, you're going to find multiple AirDAP servers. This is updated. If a server is offline, we remove it. If a new one of interest exists, we put it there. There is the EDS, Environmental Data Service Model Viewer, where you can find multiple models, especially in the US area. And you can explore multiple threads catalogs to find WMS or Opendap servers using the Siphon package from Unidata. I have a few extras. How are we doing on time, Paige?
It's Joseph now. We actually have a decent bit of time, 10 minutes, I think.
Awesome. Thank you, Joseph. So how does this all work? Well, I've been saying standards a lot. So yes, all this works thanks to standards, right? If we follow CF rules or other set of standards, we can build tools around them to easily find data, slice, and dice. And I have here just a very quick example on how we use these standards in our advantage. So this example here to get the data from the Piratas buoys, it's actually on the Piratas webpage and on their documentation, if I'm not mistaken. I apologize for those who read the ECIP talk recently because I used the very same example there, so you know this already. But you have the Opendap URL. You feed it into the netcdf4 Opendap reader. You slice the temperature and you get all the data. You slice the time, not the data, just the object. So you can actually use the object metadata and another library called CFTime to transform the numbers into high-level dates. And suppose you only want the year of 2008, you create this sense masking here, and then you use that mask to slice the data for 2008 only, and then you finally plot. That's a lot, right? That's a lot of imports here, like 3 imports, because this one is used to label the dates. Many lines of code, very error prone. I skipped this one where we are getting the bad data and mark them as not a number and all that. There must be a better way, right? And there is, because the metadata is in there. And it's all CF metadata too. So we can import X-ray, load the URL, slice the temperature, request the very first depth, 2008, and plot it. And you see the dates are here automatically. The Nora numbers were masked automatically. All the metadata on the axis, like this is temperature, and this is the depth at the first meter, got here automatically. So we are leveraging a lot here thanks to the CF standards or the what we call NUG, the NetCDF user guide for metadata. I could actually go one step further and do this as CF X-ray object instead of using the temperature variable, using the standard name for temperature. And then we could be even better. Like I would not have to guess the variable for temperature. I hope you can enjoy how much easier, readable, and less error prone this is. And if you are producing data, remember, try to follow the metadata rules. All right, I have a few more extras and I'm gonna go over them until Joseph tells me to stop or if there is a question. So another extra that I have is how to load NetCDF files directly from HTTPS. So suppose you have a bucket like on Amazon or on Google and you throw your data in there and you have a way to access them, to serve them through HTTP or HTTPS. In the past, if you try to access that with an etcdf reader, it would error out because it thinks this here should be an Opendap server, and it's not. It's actually data that you can download if you click on it. So now with latest netcdf, you can do this mode equal bytes suffix on the URL. This will do a range request. So now you can actually download data that's laying around on HTTP, lazily load them into a netcdf object. And this is, for example, the metadata, like the summary metadata for that particular data set. This is super handy to create like a Postman server very quickly if you just have data laying around on an HTTP server on a cloud somewhere. Thanks to magic. That's how this is possible. Actually, thanks to Unidata developers who implemented this in the latest netcdf library. All right, so this one is not a slideshow. Well, these are all notebooks, but this is not in the slideshow format. If we have data, we need to curate this data. We need to clean it up. We need to be sure to QA/QC it. And this is just one example on how we can do that using the Quartod rules. This is a library called IUSQC that's all based on the Quartod manuals. And what I like about this library here is that you can create all the rules and then reuse them for many different data sets. Because the Quartod QA/QC, they're pretty generic. They're the very first thing you do on the data. They're like almost near real-time QA/QC. So say you have like a growth range test to be sure the values are within an acceptable range. You have a flat line test to be sure the data didn't flatline due to a sensor failure, and some spike checks. When I configure my tests, I can perform all these tests on all the buoys and everywhere. Here, I'm going to download some data from a special OceanHackWeek server that has faulty data, and then I'm going to run this QC and plot it. And here's what we have as a result. So for the growth range test, we have a few that are marked as suspect, like yellow is suspect, red is failure, and green is good. For the spike test, we have a few that are marked here as bad. The spike test is based on a near neighbor. So you can see like the first spike here was marked as suspect, but the second was definitely marked as an error. So no test is silver bullet, right? We need to use them in tandem, because when I add this suspect with this suspect, I can pretty much say that this data point is bad. Then the flatline test, you should mark all the flatlined. Here we have a small flat line as well. I need to rerun this notebook if I want to zoom in there, but it's a tiny one. I lost my JavaScript, but believe me, there is one in there. I just need to be able to zoom in. Let me see. All right. There you go. There's like a small flat lining in there. Okay. Last but not least, pretty much like survey, we have ArgoPy, which is another model that's built on top of AirDAPI that hits a curated list of AirDAP servers. In this case, the curated list is all for Argo data. And we can do high-level queries as well, because it's using AirDAPI under the hood. The same thing applies. A bounding box, you get the Argo fetch time span, and I load that region as data frames here. And here, just for fun, I created a very fancy animation that show the Argo data at the bottom and at the surface. This is the temperature from that Argo throughout the years. And within this time range here, I completely forgot the time range that I chose, from 2009 to 2020. And this kind of plot is nice because we can see deviation, like if it's warming or if it's cooling and what's happening. We definitely see a lot of variation at the surface, not too much at the bottom, things like that. This is just for show. The plot per se is not that informative. For example, I'd love to know what's happening here, like why it's getting so much warmer here, but we don't know the year, we don't know anything. But as a quick exploration, it's pretty nice. Last but not least, like I said, if you have a curated list of server, in this case it's for Saildrone, you can hit several servers. In this case, I actually hitting only one, but you could hit many ones with the multiple ORDAP search and download Saildrone data. Saildrones are pretty cool devices. If you don't know them, they are like gliders, they're autonomous vehicles, and like Argo as well. And they have the solar panels to power themselves. They have a sail, and you can navigate them to go to hurricanes and places where you don't want to go. This is Puerto Rico, and this one was actually sent towards a hurricane. This data here, let me see if I can still get some oceanographic insight. Like you can see that this is a bit warmer, but as the Saildrone comes closer to this area here, it gets cooler, probably because when the hurricane passed, it sucked the warmth from the surface and exposed colder water from below. I'm guessing here completely because I don't have the hurricane path, but I believe that's it. All right, that's what I had. And I'm going to stop sharing now, and I can answer more questions if we have any.
There doesn't appear to be any questions on Slack or in the chat. So thank you, Filipe. It looks like we have a break next for 15 minutes. So I guess we'll take a short break right now, and then we'll come back to Jonathan talking about data access with R.